So in today's video, we're going to be focusing on radicals for assignment 14. And before we start with radicals, I kind of want to review some of the basic vocabulary. But I think even before that, um, some people told me that they were still struggling with exponentials. So let's have a little bell work first. Um, and why don't you try simplifying the expression? And so our expression this time is going to be 6 squared times x to the third y to the negative 3 over 12x to the minus 2y. So take a moment to simplify that exponential expression and probably pause the video and come back when you're done or want to check your work. Okay, so 6 squared is 36. And then here, it's x to the third minus a minus 2. And y to the minus 3 minus 1. So if I tidy each of these up, 36 divided by 12 is 3. 3 minus a minus 2 is going to be x to the fifth. And negative 3 minus 1 is going to be y to the negative fourth. Remember, if the directions say no negative exponents, we need to take this a little further. 3x to the fifth over y to the fourth would be my simplified answer. Okay, let's do one more, and then we'll move into radicals. 3 to the negative fourth, m to the negative 1/2, n to the negative 3/4 over 9 to the negative 2, m to the 1/2, n to the negative 5/4. So give this one a try. Pause your video, give this one a try. See how it goes. I'm hoping that this is more comfortable for you than it was a few days ago. Welcome back. So, these students like to move. And they like to move all these negative ones also. But I'm just going to do negative 1/2 minus 1/2 and n to the minus 3/4 minus a minus 5/4. Now, curiously, here I have 81 over 81. So they cancel each other out. I end up with m to the negative 1, n to the minus 3/4 plus 5/4 is 2/4. Or square root of n over m. Right? This one can go to the bottom. This simplifies to n to the 1/2, which is square root. You could certainly leave it like this. That would be fine too. Okay? Remember, if you have more questions on simplifying exponential expressions, post them in the group me, send me a message, ask during our Zoom sessions. But now we're going to move on to radicals. There's a little vocabulary associated with this. So that's the radical sign. And what's under the radical, that actually has a name. That's called the radicand. People who get tired of saying the stuff under the radical, they say radicand. And then the number here, not the coefficient, but the little number here, like 3, that number is called the index. Okay, and we know that the domain is negative infinity to infinity when the index is odd, but we know that the domain is 0 to infinity when the index is even. Okay? So let's, sort of visualize this the same way we did visualize revealing our rules for exponents. Let's start with, let's envision this as 5 rounds of different classes of problems. And the first ones are just really basic simplifying problems. So here's the first one, square root of 24. You've been simplifying radicals like this since middle school, and if you're not comfortable with it yet, you really need to be comfortable with it now. So this is going to be, make a factor tree for that. 2 times 12, 2 times 6, 2 times 3. So 2 times 2 times 2 times 3. And with a square root, the index here is 2. So it takes 2 of a kind to get 1 out. 2 square root, and these are left over 6. Okay? So will you simplify this one? Please simplify that. So when you did the factor tree here, did you get 7 times 7 times 2? So we've got a pair of 7s that we can take out, and we have 7 root 2. How about square root 121 n squared? Well, that's a perfect square. That's a perfect square. And so, we can think about it as 121, as 11 times 11 times n, in which case we can bring out an 11, we can bring out an n. There's no one left under the radical, so that can go away. So we have 11n. Well, at least that's probably what we learned in Algebra 2. And, for our class, that's going to be okay too. But when you go look up the answers to this, the answers in the back of our textbook aren't this. They're similar, but different. They're that. So the square root of n squared is not n. The square root of n squared is absolute n. And so, those of you moving on to calculus, we'll talk more about this for sure next year, and we'll need to be focusing on those absolute values. But, it's still pretty casual in pre-cal. You can get away with saying the answer to this problem, or the simplification of that problem, is simply 11n. All right? But what makes these different? Well, this is a variable. This is a number. This is a variable. Variables, for those even indices, they get the absolute value. Okay. Where are we now? How about we do this one? Well, I hope when you did the factor tree on 48, you had 4 times 4 times 3, and then we had n to the third. Now, I know this is a square root, so it takes 2 of a kind to get something out. Some people broke this down into 2 times 2 times 2 times 2 and took out 2 pairs of 2's. That's fine too. I'm just going to take out one of the 4's and one of the n's and have 4n square root 3n. That's the fine answer, but the back of the book answer is going to be this. Okay? So what changes when we do this? Well, now it takes 3 of a kind to get something out. 2, 2, 2, because 2 times 2 is 4, times 2 is 8. Hey, look, I have 3 of a kind. I can take a 2 out. There's nothing left under the radical, so we get rid of it. So cube root of 8 is 2. What can you do with the cube root of 27 x squared y to the third? Please simplify that expression. Okay, so we know that's 3 times 3 times 3 times x times x times y times y times y. I can take out a 3 and a y because my index is 3. Don't lose that. It's there. It's got to be on your answer. And these can't come out because I don't have 3 of them. So I'm just going to go back to x squared. There's my simplification. All right. How about this one? Cube root of 54 a to the third e to the 7th. So 54 breaks down into 2 times 27, and we know that 27 is 3 times 3 times 3. We've got a to the third, and b to the 7th. You know, I really don't enjoy writing these all out. And if you don't enjoy writing them all out so that you could find groups of 3, you could just say to yourself, hey, how many times does 3 go into this? 2. So I've got b squared on the outside. 3 goes into this once, so I have an a on the outside. And I've got those 3 3's coming out, the 3 coming out from these 3 3's under the radical. Okay, what's left? Well, remember when we said 3 goes into this twice with 1 left over? Well, we've still got that 1 left over sitting under the radical, and we have happy 2. Hi, happy 2. Okay, so there's my simplification. Now, let's move to more thoughtful and harder problems. How about a square root of a plus b? Hey, will that be the square root of a plus the square root of b? Well, you know, let's test that idea. All right, so I'm going to say that a equals 4 and b equals 5. Okay, so then that's going to be the square root of 4 plus 5, which is the square root of 9, which is 3. But on the other side, we're saying that's the square root of 4 plus the square root of 5. And that's going to be 2 plus root 5. Does 2 plus root 5 equal 3? Well, you may be saying, but I don't know what the square root of 5 is. Well, you know the square root of 4 is 2. And this is bigger than the square root of 4. So this is going to be bigger than 2 plus 2. Does that equal 3? No, it does not. This rule does not exist. This is not equal. This is I chase you with a pool noodle. If you try and do that kind of horrible math, don't do that. Now, if I had square root a plus b squared, well, that's, 2 of a kind being multiplied together. I can take one of those out, a plus b. But remember, we've got this variable here. I'm going with that. You can go with this. That's fine. Okay? So what are you going to do with this problem? A squared plus 2ab plus b squared. Now, I will tell you at the start, it does not work to do this. We just showed that you can't do that in the last problem. So don't try it here in this problem. We already said you can't do that. Don't do that. Instead, you can say, oh, well, that's a plus b times a plus b when I factor that trinomial. And look, I can get an a plus b out of that because I have 2 of them being multiplied together. Okay. With that in mind, we were able to factor, just like we could here, x squared minus 4x plus 4. This factors as x minus 2 times x minus 2. I've got 2 of a kind, and so I'm going to take out that x minus 2. What about square root of a squared minus b squared? We know that factors. It's a minus b, a plus b. Can we do anything with that? Well, a lot of students want to tell me that the answer here is a minus b, and it isn't. And some students want to say it's a plus b, but it isn't. This is different than that. Are these the same? No. Do I have two of the same thing like I had here? No. So the answer is I can't simplify. I can't simplify. Again, this isn't going to be the square root of a squared minus the square root of b squared. It's not going to be that. So please, many of you make this kind of mistake. Don't do it. Pay attention now. Use this as a learning opportunity. Don't do it. All right. That's the end of round one. We know that some things we can simplify even when we have a plus or a minus in there, but other things we can't simplify. Can't simplify that because I've got a times a plus b times b, and I can't pull stuff out with this. Here, all of that was inside the squaring. All of that was simply telling me I had an a plus b times another a plus b, two of the same things being multiplied together. Well, sure, I got two of the same things being multiplied together, but it's attached with addition to these things. No, can't simplify. Sorry. And the only way to simplify, to factor this, is using imaginary numbers, so I really don't want to get into that. Okay? So we say can't simplify. All right, round two. Round two has us looking at products. We're multiplying with radicals. So, square root of 10x squared y times square root of 40xy to the third. Now, what we can do, because this is multiplication and because these have the same index, and yes, they're always going to have the same index in our class. If this were on the free count, we'd mix it up. We'd have a squared here and a cube here, and that would be just fine. Okay, so what are we going to do? We're going to take all of this and put it under one radical. And then tidy things up. We've got 10 times 40, which is 400. We have x squared times x, which is x to the third. We have y times y third, which is y to the fourth. And now we can simplify this radical. Did you remember that 400 was 20 times 20? So I can take out a 20. I can take out an x because I've got 3 of them and I only need 2 to get one out. And, oh look, this is y squared times y squared, so we can take out a y squared. What's left? Well, we took out all of this, we took out all of this, and we got 2 of the 3 of these, so we still have an x there. Okay? So multiplying radicals can often mean just pack them all under one radical sign and simplify them. Okay, with that in mind, will you do this one? 12m squared n times square root 6 n squared. Okay. Pause the video, give this one a try. Welcome back. So under one radical, 12 times 6 m squared times n times n squared. Now, I didn't turn that into 72, and there's a reason for that. 72 means I'm just going to have to build a big factor tree to figure out what makes 72. And here, I already see 12 times 6, and I know that 12 breaks down to 2 times 6, so I've got a pair of 6s. And so I might want to think about this as 6 times 6 times 2. I've got n to the second times n to the first, n to the first times n to the second. And now when I go to simplify, I pull out 6, I pull out an m, I pull out an n, and I'm left with one of these, and one of these. 2n. Okie doke. How about this? 2 root 2 times 4 root 6. Well, here, the coefficients can be multiplied, and the radicands can be multiplied. So I'm going to have 8, and then under the radical, 2 times 6. I know that 6 is 2 times 3. Well, look, a pair of 2's. So the 2 comes out. How is the 8 attached to the radical sign? Well, I don't see a little plus or minus there. So that's multiplication. So this 2 gets multiplied times that 8 to make 16, and we still have a 3 underneath the radical. Okay, with that example in mind, how do you think this works? This is distributing. 4 root 3 times root 27, 4 root 3 times 4 root 3. Well, let's take each of those pieces one at a time. We have 4 root 3 times root 27 plus 4 root 3 times 4 root 3. Okay, so we know that 4 times 4 is 16, and then we have root 3 times 3. Hey, we've got a pair of them under that radical, so we can bring that 3 out. And that's going to give me 48. What about over here? Well, we said before that we could put both of these under the same radical, and we know that 27 is 3 times 3 times 3. Well, there's a pair of 3's, there's another pair of 3's, so I can make this be 4 times 3 times 3, and there's nothing left under the radical, so I can make that go away. So we've got 9 times 4. 9 times 4 is 36, plus 48, 70, 84. I think it's kind of interesting that something like this can simplify to that. It's kind of elegant. All right, so we've got distributing, and you know what else you can do with radicals? You can FOIL them. Will you try foiling this one? Pause the video, give it a try. Welcome back. First, outer, inner, last. Okay, so we've got 15. These are like terms because they have the same radical, so minus 5 plus 3 is going to be minus 2 root 3. We have minus 5 of them plus 3 of them, so now we have negative 2 of them. Okay, and then here we have square root of 3 times 3, which is 3. So 15 minus 3 gives me 12. And that's what you should get for that one. Let's try one more of those as our last round 2 problem. 6 plus root 2, 6 minus root 2. Okay, give that one a try, pause the video, see how it goes. All right, so when you FOILed, 36 minus 6 root 2 plus 6 root 2 minus root 2 times root 2 is 2. So 34 is my answer here because these middle ones are opposites and cancel each other out. Yeah, that's how that one goes. Okay, so round 1 was simplifying, round 2 was multiplying, round 3, quotients. So I'm dividing. I'm dividing in round 3. So let's start with something like this. You know, when you have something like this, you can actually split it up into this and this and get 1/3. That's probably the easiest thing to do there. Likewise, if you have something like 9 over 81, you can simplify inside of there first before, like you don't have to break these up like we did here. You could actually simplify under the radical. You know, that could be useful if you have oh, there we go. 4 over, oh no, that's exactly not what I want to show you. It could be useful to do this if I had 54 over 27. So that goes in twice, and so I just have square root of 2. I don't need to split this up into two radicals. I think it's more work in this problem to split these up like this, and then to simplify them 3 root 6 over 3 root 3, and then you have root 6 over root 3. And what am I going to do? Well, I'm going to put that all under one radical, and that's just going to be the square root of 2. And to me, that's a lot more work. Sometimes splitting the radical up into a top radical and a bottom radical makes the problem easy. Sometimes splitting into the top radical and bottom radical makes the problem take a lot longer, and you should have just simplified while they were under one radical. What would my advice be? My advice would be see if you can simplify under the one radical before you split into two radicals. Okay? Now, let's take a look at the square root of 4 over 5. So that could be the square root of 4 over the square root of 5, because there's no simplifying I can do here. And I know the square root of 4 is 2. And that brings us to the radical in the denominator place. All right? So the radical in the denominator place is kind of problematic for older people. Older people grew up with a thing called the slide rule. And these people that, when I was in high school, our teacher showed us how to do the math on a slide rule, but we had calculators, handheld calculators. So we used those. But, you should really go watch a YouTube video on slide rules and how they work, because they're really freaky amazing. It's essentially just a ruler with a middle thing that you can slide back and forth, and they had a little thing on here with a line on it so you could actually read the numbers carefully, because the numbers are so small. But on a slide rule, you could actually do all kinds of math. I mean, pretty much everything on your four-functioning calculator, including trig and logs, you could do it on a slide rule. In fact, slide rule is what the engineers who sent the astronauts to the moon used to do their computations. So here's the thing, though. As amazing as the slide rule was, there was one thing the slide rule could not do. And the one thing the slide rule could not do was divide by a radical. So, for, 100 years, kids in math classes were told they can't have a radical in the denominator. And that's because the slide rule can't do that problem. So we taught kids how to rationalize the denominator. And this is round 4, rationalizing. We want to get rid of the radical in the denominator. And so we have 2 root 5 over 5, right? Because we have 5 times 5 under the radical, and 1 can come out, and there it is. Look, no more radical in the denominator. Well, I don't know if you've noticed, but your new calculator that is not a slide rule doesn't have any problem whatsoever with doing 2 divided by root 5. So we don't actually need rationalizing anymore like we used to. I will say that you still need to know how to rationalize. But Mr. Kukla, you just got through saying that we don't need it anymore. It's true, you don't need it anymore, but the people who are writing the ACT, the people who wrote the U of A math placement test, those people, they grew up rationalizing these. And for those people, you still have to do this. You still have to rationalize. Okay? So whatever that radical is, I multiply top and bottom by it. Well, almost always. 2 root 5 over 5. Let's change this problem a little and have 2 over cube root of 5. See, because now, how many 5s do I need to get 1 out? Well, this says I need 3 5s to get 1 out. So I have to multiply by the cube root of 2 more 5s, because I need a total of 3. So this is the cube root of 25. 2 cube root 25 over cube root 5 times 5 times 5, or 2 cube root 25 over 5, right? I've got 3 of them. I need 3 to get 1 out. There they are. But that's a 3. And so even though I'm tempted to say, oh, square root of 25 is 5, that's cube root of 25, which is not 5. Can't take 3 5s out of that, so I'm stuck. Okay, that's as far as I can go. All right, so why don't you practice a couple of these rationalizing problems? How about 2 over root 6? Please rationalize there. All right, welcome back. Did you get 2 root 6 over 6? And then notice that you could cancel there and have root 6 over 3. You can't cancel the 3 in here with the 3 down here because this 3 is under the radical and that 3 is not. If they were both under the radical, yeah, you could cancel. If they were both not under the radical, yeah, you could cancel. But one is under the radical and one is not under the radical, and so you cannot cancel there, okay? All right, how about this one? 5 over 2 root 3. Pause the video, give this one a try. Okay, welcome back. So I don't need to do anything with the 2. This is the thing that needs to be rationalized. This is the thing that I need to get rid of. And so that's the thing that I'm going to multiply top and bottom with. So we have 5 root 3 on the top. On the bottom, root 3 times root 3 is 3 times 2. And so we end up with 5 root 3 over 6. Okay. I think that's all I wanted to say with that one. All right. So then, here we go. How about 1 over cube root of 7? Please rationalize that denominator. Welcome back. So this says I need 3 of a kind, and right now I only have 1. So I need to multiply by 2 more 7s. 7 times 7 is 49. So this is cube root of 49, and then I have 1, 2, 3 7s on the bottom, so I can take a 7 out. All right, so, you know, this is all about rationalizing the numerator, getting no radical, rationalizing the denominator, getting no radical in the denominator. And like I said, since we don't use slide rules anymore, we don't really need that. However, there is a type of rationalizing that we do need. And that's actually rationalizing the numerator, getting the radical out of the numerator. There's some calculus stuff that some of us will be doing next year where we don't want the radical in the numerator. And so we're going to have to rationalize to get rid of it. Root 2 times root 2 is 2 over 3 root 2. And this is going to be okay. We're going to be happy with this. I know we've got a radical in the denominator, but trust me, in calculus, we'll be happy campers with that and not happy campers with this. So rationalizing the denominator, rationalizing the numerator. If it doesn't specify rationalize the numerator, you know you're rationalizing the denominator. That's by far the most common. Okay, I'm almost but not quite done with rationalizing. We talked about rationalizing when we had one even index root here. We talked about rationalizing when we had an odd index root here. In fact, let's try this one. What if that's a 4? Give this one a go. Now, did you do this because you said you had 1, 4? And so now you've got 2 cube root of 16 over 4. But wait a second, cube root of 16, you can take 2 out of there, right? Because root 16, cube root of 16 is 2, 2, 2, 2. You can still pull a 2 out. And so we have 2 times root, cube root 2 over 4, and those cancel, and we have cube root of 2. See, that's the long way to do the problem. You saw 1 4, so you multiplied by 2 more. Do you know what I saw when I did this one? I saw 2 2's. So I just multiplied top and bottom by cube root of 2. So on top, I have 2 cube root of 2, and on the bottom, I have 2 times 2 times 2 under that cube root, so I pull out a 2. So it's less work to see this as 2 2's rather than 1 4. You can still get there by multiplying top and bottom by cube root of 4 times 4, but not without a lot more simplifying. Okay, so the last type of rationalizing we need to look at is what happens when we have a binomial on the bottom, 2 terms on the bottom. Everything we've looked at so far was just 1 term on the bottom. So let's try our default. Let's try multiplying top and bottom by root 3. Does that get rid of the radical in the denominator? Well, when I distribute here, root 3 times root 3 is 3. Well, that's great. But root 3 times 1, yeah, that's root 3. I still have a radical in the denominator. And by all the gods of Norse mythology, do not cross these out. That is so bad. So very bad. Bad, 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 bad. If you could take out a root 3 from all of them, you can take out a root 3. But you can't, and so you may not. Cancel on top and bottom. So if this had a root 3, I could factor out root 3 on the bottom and have 1 plus 3, and then I have 3 root 3 on the top, and they can cancel, because these are attached with multiplication. But that's not what I'm looking at here. You cannot cancel these out. It's really time to learn that. I mean, people have been trying to tell you this for years now. Okay? Don't let it continue if you're making that mistake. All right, so multiplying top and bottom by root 3 did not get rid of the radical on the bottom for us. So we need to do something else. And the something else we need to do is called multiply top and bottom by the conjugate of the binomial. Okay, so tell me about conjugate. Well, conjugate of root 2 plus root 3 is root 2 minus root 3. The conjugate of 4 minus root 5 is 4 plus root 5. I'm not changing both signs, I'm just changing the interior sign. And why am I doing that? Well, I'm trying to get the situation that creates something that looks like the factored form of a difference of squares. And the reason I want to do that, the reason I want to multiply top and bottom by the conjugate, the reason why I want to multiply by something that makes this turn into a difference of squares is because when I FOIL here, what happens to the middle terms? Well, I have a plus root 3 and a minus root 3, and they cancel. And that's what gets rid of my radical, creating a difference of squares so that the middle term goes away. On the bottom, then, I just have 1 minus 3, which is negative 2. On top, I've got 3, 1 minus root 2. I'm sorry, root 3. Now, what I would say is hold off on distributing that for a second and see if you can cancel between top and bottom. Here I can't, so you could either leave your answer like that or turn it into this, which I guess could also be because I moved that negative up to each of these. But yeah, I would check that first to see if there's any canceling there before distributing. Okay, so rationalizing the denominator using conjugate. Here's yours. Will you please do 5 plus root 2 over 3 plus root 2? And oh my God, you cannot cancel these out. They're attached with plus to these things. Stop it. Don't do that. Okay, you know what you're supposed to do here. you're supposed to rationalize the denominator using the conjugate. So pause the video and give this a try. Try rationalizing the denominator. Come back when you're ready. Okay, welcome back. Our conjugate, 3 minus root 2, 3 minus root 2. So when I FOIL on the bottom, 3 times 3 is 9. I get minus 3 root 2 plus 3 root 2, and then minus root 2 times root 2 is 2. On top, I get 15 plus 3 root 2 minus 5 root 2. Root 2 times root 2 is 2. Positive times negative is minus. So we can tidy things up. 15 minus 2 is 13. 3 root 2 minus 5 root 2 is negative 2 root 2. And on the bottom, these middle terms cancel each other, and we have 9 minus 2, which is 7. Is there anything I can GCF factor out at the top so I could cancel with that 7 on the bottom? No, I don't see anything there either. So this is as far as we're going to go. All right, so there's rationalizing the denominator. What about one last rationalizing? 2 minus root 3 over 5. All right, so that is a radical in the numerator. So why don't we rationalize the numerator here? And we're still going to use the conjugate on top and bottom. But our goal when we rationalize the numerator is to get the radical out of the numerator. Okay, so I FOIL on top. And I'm going to hold off on distributing on the bottom. I'm probably going to do it, but I'm going to wait until I'm done tidying this up. So these cancel. 4 minus 3 is 1. No, there's no canceling. You know, you could just leave it like this in its factored form, or you could distribute and have 10 plus 5 root 3. This would be a fine answer to me. This would also be a fine answer. This is just a little more work because it includes one more step. Okay, so there was round 4, rationalizing. Now, what about adding and subtracting? Okay, so we want to talk about adding and subtracting radicals, and we can only do that if the radicands, the stuff under the radical sign, are the same. Okay, so let's take a look. 5 root 2 plus 3 root 2. The radicands are the same, so I can add these. 5 of them plus 3 of them gives me 8 of them, okay? Same thing with subtraction. The radicands are the same, so 5 of them minus 3 of them gives me 2 of them. Okay, well what happens if I have a situation like 3 root 7 minus 5 root 28? The radicands aren't the same. Do I just write can't subtract? Well, let's pursue this a little more. Can we simplify this radical? Isn't 28 4 times 7, so 2 times 2 times 7? Can't I take a 2 out? So this will be 3 root 7 minus 5 times the 2 that comes out, 10, root. What's left over? A 7. Oh, look, they are the same. 3 minus 10 gives me negative 7 root 7. So yes, I need the radicands to be the same, but if they're not the same, don't just walk away. Ask yourself if you can simplify so that they do have the same radicand. All right, so what about this one? Square root of 98 minus square root of 72 plus square root of 32. None of them have the same radicand. Does that mean we can't do the adding and subtracting? Try simplifying. Try simplifying and then see if there's any adding and subtracting you can do. Pause the video now and give it a try. Well, welcome back. Did you get 7 root 2 minus 6 root 2 plus 4 root 2? I did, and I see that the radicands are all the same. 7 minus 6 is 1. 1 plus 4 is 5. There's my answer, 5 root 2. Okay? So let's add some variables to this. How about cube root of 16a plus 4 times cube root of 27a? I know they both have an a, that's good, but these aren't the same, and I could only add if these are the same. Is there any simplifying I can do here? Why don't you try, pause the video now, give a try simplifying, and see if you can still do some adding. Notice that these are cube roots, not square roots. Okay, welcome back. So this is what I'm looking at. And I say, oh look, I can take out a 2, and I can take out a 3. So I'm going to get 2 cube root of 2a plus 3 times 4, 12 cube root of a. Can I combine these? No, I cannot. So that's as far as I go. All right, now if I had instead here 54, well, that would be 3 times 3 times 3 times 2, and then I would have that 2 left over, and I could combine these to 14 cube root 2a, okay? But I didn't. I had 27, cube root of 27. So pay attention to what you're doing. Be thoughtful, be mindful when you go through these problems. How about this one? 5 cube root 40x minus 7 cube root 5x. Okay, anything we can do here? Well, how about simplifying this? This is 2 times 2 times 2 times 5. So it looks like we can pull a 2 out. 2 times the 5 that's already there. What's left? A 5 and an x. So once we're done simplifying, do we have common radicands? We sure do. So then we can just do 10 of them minus 7 of them gives us 3 of them. Okay? All right, so there we reviewed radicals. You know, most of my time when I see something like radical 2, yeah, I like using that because when I see this, well, where is it? If I have, for example, this square root of 2 over cube root of 2. That's a real pain to work with. You know, I have to multiply top and bottom by the cube root of 2 more 2's, and then I have to figure out how these two play together, and they don't play together well. I have to do all kinds of things, and really what I want to say is, look, if I took this and turned it into rational exponents, I'd have this. And then, when I'm dividing and the bases are the same, what am I supposed to do with these? I'm supposed to subtract them. 1/2 minus 1/3. And so, what do I need now? Well, my middle school math teacher said I need a common denominator. So 3/6 minus 2/6 is 1/6. So I can get to 1/6 without using any radicals. So, you know, I try and minimize my use of them. I would much rather use rational exponents, especially if I'm going into calculus. Rational exponents are easy to work with in calculus. So 2 to the 1/2, we have smiley face. Radical 2? Ugh. Okay, so will you take care of this one? Cube root of y squared times 5th root of x to the 4th over 1 over cube root of y squared times 5th root of x. Okay. See, in my mind, this is horrible. Just horrible. And instead, what I want to do is I want to turn these into rational exponents. Okay, so this one is y to the 2/3. And this one is x to the 4/5. And this one is 1 over y to the 2/3, or y to the negative 2/3. And this one is x to the 1/5. Now with rational exponents and the bases are the same and I'm dividing, I just subtract the exponents. And so I end up with y to the 4/5 times this minus this, x to the 3/5. If I had to put my answer in, that's 4/3. There. So I like that. That's fast simplifying. It's much better than dealing with how do I put these all under one radical? What do I do with this thing down on the bottom? Turn them all into rational exponents, which is why, one of the reasons why we looked at rational exponents before we looked at radicals. I mean, I would like you to be able to see this problem and say, oh, I can simplify this expression just using, that's an 8, my rules for exponents. When the bases are the same and I'm dividing, I subtract the exponents. Minus 1 is going to be x to the minus 2. Bases are the same and I'm dividing means I subtract the exponent. 2/3 minus 8/3 is negative 6/3, or negative 2. And then here, look, the bases are the same, so I can subtract. Minus 3 minus a minus 1 is minus 2. And so I have 1 over x squared, y squared, z squared. Okay? Be comfortable with simplifying radicals, but be even more comfortable working with rational exponents. Okay, so you've got bookwork, as I recall, tonight, so you should take care of that. You'll find, of course, the scanned pages in our Office 365 team folder. All right, take care, everyone.